Welcome back my dear friends and dear students. This is the DADM 2 lecture series under NPTEL MOOC, and as you know, this total course duration is 30 hours, which is for 12 weeks, and each week we have 5 lectures, each being for half an hour. So, total duration would be, as you know, 30 and spread over the total duration. I am Raghunandan Sengupta from the IME department, IIT Kanpur. Now, coming back to the discussion, if you remember, we were discussing the safety first principle, and I did mention that how the normal distribution being true, how we can solve it very easily. So, we will continue discussing that, and this is the 10th lecture, which is the last lecture in the second week for DADM 2, and after that you will have the second assignment. So, even though for our example, we have simplified our assumption by considering only normal distribution, this point which I mentioned time again, but this would hold true for any distribution having the first and second moments, because the reason being first and second moments being you need to find out the expected value, you need to find out the standard deviation or the variance, which is basically for ABC decisions. R bar A, R bar B, R bar C would be the respective mean values for ABC decisions, and similarly sigma suffix A, sigma suffix B and sigma suffix C would be the corresponding standard deviation for ABC decisions. I am using sigma in place of standard error, but that is without much of concern, because if you get the concept you can solve it accordingly. Now, I did mention about the Chebyshev's inequality and Markov inequality very fleetingly, I do remember, in the case of DADM 1, and try to utilize that concept for the DADM 2, where you have the safety first principle. So, according to Chebyshev's inequality for any random variable x, such that first moment and second moment, which is E of x and V of x exist, then obviously you will have this as true. Now, let us look at from the diagrammatic point of view, so that if I am able to draw the diagram, it will be easy for me to explain to you, and also you will get that concept decently clear. So, I will first draw the normal distribution. I will use the axis as black. So, this is the normal. Now, I have the expected value, which I will mark as red. So, the E of x, so it can be RP also, R bar P, R bar PA or PB, what I am using the expected value, and there is a variance. Now, this x has a distribution which is normally distributed, and what I am considering is that a bandwidth depending on the variance. So, consider this one. So, this is the value. So, I am considering x minus Ex divided by Vx. So, I am basically normalizing the difference between the random variable and the expected value divided by the variance. So, the variance being very high, obviously it will be normalized accordingly. So, I want to take this whole area and that is greater than some value of t. T is a so called constant which I will take, and the value of that would always be less than equal to 1 by t square depending on the Chebyshev's inequality. So, what I do is that in this case I replace x by Rp, E of x by Rp bar, and there was a variance also, I did not write it, f of V of x would be replaced by sigma, actually should be sigma of Rp. So, and you consider a value of k, k would be the some threshold value. So, that probability would be for this mod of this normalized distance being greater than k would always be less than equal to 1 by k square. So, higher or lower the k square will dictate that what is the so called normalized length based on which you can take this decision. So, if you basically have two or three different type of distributions, these are not normal. I am using the word two or three different type of distribution based on the fact that the mean values and the variances for the decisions are different. So, say for example, you have A, you have B, you have C. For all of them, you will basically have such distributions where the expected values and the variance are different. Based on that, when you find out the Chebyshev inequality, you will have some value of k, and being less than equal to 1 by k square would give you the bound such that you can find out that how you can rank the decisions based on the safety first principle. So, as we are interested in lower limit, that means we are interested more on the negative values. If you remember, it was basically minimization of probability of R p is less than R L. So, simply we can write down. So, if it is we remove the mod, so we find out the value. So, in place of in place of x it will be R p, in place of E of x it will be R bar p, and in place of variance of x it will be sigma of p or sigma for R p. So, this is greater than k such that is less than 1 by k square. Now, what I do is that again I now normalize them. So, normalizing this basically means, okay, now coming back to the actual formula. So, here this actually this is coming from here, and then I will write down what I am missing, and then I jump here. So, if you remember, we already have this formula. I should use a different color, it will be easy for us to differentiate. I will highlight it first. So, this is the so, let me write down what is the actual thing which we were looking for. So, we already have seen in the previous discussion. So, the equation which is written here where I am hovering my pointer is actually R p minus R p bar divided by sigma of R p. This was greater or equal to, so in this case it is greater. Now, you already had R L minus R p bar divided by sigma of R p. So, now what we do is that we are replacing this with k. Sorry, so this is k, I should remove it, k. So, which means that the k value is known to you given the fact that the standard deviation and the values of R n and R p bar are known to you. So, R L technically would be, and use the red color. So, actually this would be R f. So, you have the standard deviation of the decision, the mean value of the decision, and R f being the risk free interest rate which is coming from outside. So, immediately you can find out the bound k, k square, and solve the problems accordingly. So, lower and higher would basically give you how you can rank them from the highest to the lowest or the lowest to the highest depending on what your main criteria is. So, the right hand side of the inequality is in exactly equal to the decision process 1 which we have taken. 1 means minimization of the probability of R p less than R L under the safety first principle. So, we have considered initially. So, once you basically put this, technically this is k, this is k square. So, actually the whole formula leads to the first safety first principle or bullet point which you have considered. So, technically the Chebyshev inequality and the safety first principles are the same considering the normal distribution, and similarly you can modify that rule of the safety first principle, the first bullet point with respect to the Chebyshev accordingly, provided if you remember I mentioned the first moment which is the expected value and the second moment which is the variance exist. For the second criteria, if you remember, now I am basically trying to change the problem. I am not going to solve these problems from the optimization point of view. Remember that we will only come into this optimization concept later on in DADM 3, is basically to highlight that how they can be utilized. I do not want to burden all of you with trying to solve the optimization problem, because this is a total different concept we will consider in DADM 3. For the second criteria, we already had maximization of RL. I should use the color red, so it will be easy for us to read. So, you maximize RL, and what you do is that you bring such then constraint. So, you are trying to push RL onto the right. If I am looking at the distribution from my side, RL is on the left, you are pushing it onto the right, but subject to the case that the probability of RP less than RL is kept fixed at alpha. So, obviously it will mean technically your actual optimization is, now let us think it a little bit philosophically, or let us try to understand it. When you are talking about RP, which is basically where we already have the returns and we want to find out the weights for the alternatives. Now, if the weights change, RP changes. So, when you basically look at this optimization problem, maximization with respect to some constraint, maximizing RL is basically pushing on to the right, but provided also the probability of RP is less than RL is less than alpha. So, obviously, if technically if the distribution, let me draw it. No, this is, so let me write it, this is RP bar, this is RP, this is RL. So, what you are trying to do is that you are going to push RL, but subject to the fact that this whole area remains as alpha. So, if you are pushing RL, obviously it would also mean that if only RL moves, then the area alpha will start increasing. So, in order to restrict that, the whole distribution also starts moving on to the right. So, the alpha value remains as it is. If I consider the overall value to be alpha, it can be less than alpha also. So, we are giving alpha, given alpha say for example 0.05, then we should basically have, if you convert this whole set of constraint considering the normal distribution. So, what you have is RP minus RP bar divided by sigma of RP, which is the left hand side of the equality inside the bracket, and on the right hand side it will RL minus RP bar divided by sigma of RP, which is the second term on to the right hand side of the inequality sign inside the bracket, and this alpha value is given from depending on the reliability of the overall risk attitude the person has, based on which he or she can basically invest. So, we have drawn it considering the distribution is true, what is showing being shown here for a decision B. This is basically RP bar, obviously you will have the RB as the distribution, this is RB bar, then you have a standard deviation. So, technically this Z is being formulated based on the fact that you have converted that into a standard normal. That means, you have started with this I am repeating it many times, plus please bear with me. So, this value of z is equal to this, and the value for this, which is basically the distribution of z we have been able to basically draw the distribution of capital of Z. So, technically this is the Z, capital Z. So, this distribution has been, it should be drawn. So, I have basically drawn both of them and basically marked the values accordingly. So, technically this should be some RL which has been converted to small z, this is RB which has been converted into capital Z, the standard normal distribution. And again I am repeating, this can be done for other distributions also. Now coming back to the utility concept based on the mean variance concept for portfolios or any decisions, what I would not go into the details, but I will basically highlight it. So, if you see the mean variance diagram, so along the y axis you are measuring R bar P, it will change depending on the weights which you are investing in different alternatives. Along the x axis you have sigma P, and what you are doing is that you have drawn this blue line which is the efficient frontier. So, our main task is basically to find out that P star value. P star is basically a so called optimum portfolio value, where the weights which you are trying to invest in this different type of alternatives for the decision, which is the portfolio, is such that I am getting the maximum return based on the fact my risk is also increasing, but the proportional value of the increase of the risk is such that the ratio of the risk to return or return to risk is the best for my case. So, risk to return would be I am trying to take the minimum value, for return to risk I will take the maximum value, such that the weights are the best combinations. So, what you do is that this RL value, which is RF, which is the risk free interest rate, you will basically keep changing it. So, as you keep changing it, you will basically have different contours based on which you can find out what is the best value of portfolio or the alternatives, such that you get the RP star value or P star value. So, you keep moving the parallel lines which are RL1, RL2, this suffix 1, 2, 3, 4 are the different values. So, you keep changing them. So, say for example, if you consider RL, the values which are there inside this whole set of values, or the points which are there inside the graph, are basically different combinations of risk return profile for the decisions, such that you have different type the same alternatives, but you are investing in different proportions. Now, those are not the best, because you have not been able to reach the best optimum value, because obviously you will always try to go as high as possible for RP and as low as possible for sigma P. So, keep changing RL. So, go to RL1, RL2, RL3, and the point where it is basically tangent to the graph, that P star value would give us the best combination, such that my overall risk and return profile is met. Now, you may be thinking that why I have drawn this graph in this way, they could have been other tilted also. Let me draw it. Let me use the green color. So, say for example, RAL or the graph was this, depending on the risk return profile. So, I could have drawn parallel lines like this. So, it would, the RP star would have been some value. So, for the first case I will use the return and risk were this. So, I will consider as, say for example, double star, and another case is basically and I'll remove this and come back to the same color combination. So, it is easier for me to draw. So, the first value is basically sigma P 1 star, and this is sigma P double star. Double star and 1 star are just to differentiate. Similarly, here you will have basically R P double star R value, and this is R bar P single star. So, they would basically be two different sets of portfolio or the two different sets of decisions based on the fact that the alternatives are the same, but you are investing different amounts. You can change it accordingly depending on how the problem has been formulated. So, the criteria to maximize RP such that now you are again bringing a constraint which is based on the fact that you had the first safety first principle is probability RP is less than RL is equal to alpha. The alpha value is fixed or determined or given by the investor. Here alpha is the predetermined depending on the investor's own constraint. Thus, with the condition if you put it, you will basically have the graph as this. Now, this is a simple concept. How do we do it? Let me basically go reverse step. So, basically it is RP bar minus RL divided by sigma p is less than equal greater than small z. So, this is the case. So, what we have considered is basically this should not be R bar. So, if you consider the value here, this is basically small z on the right hand side of the equation which is from here. So, you have been able to convert that actual value of RL minus RP bar divided by sigma p into a case where it is basically the small z. You put a equation for that, have a linear line, and that is the linear line we have been talking about. So, you can basically convert it depending on how the problem has been formulated. Now, consider a different way of trying to solve the problem. Here I will consider the RF or the RL is fixed. So, I want to find out at what value of RP or P star I will get the best combinations. So, what I do is that I have the efficient frontier which is the blue line. Now, what I do is that I turn the straight line which is RL and A1 is arbitrarily one point taken in order to basically denote the straight line. I turn it counterclockwise, keep moving it. So, basically it cuts or basically touches the blue line at B1 and A1, then you turn it counterclockwise, it touches or cuts the blue line at B2, A2, continue doing it. So, at one point of time A1 so these A values and B values merge, which would basically be the tangent point, and that is the P star value based on which you are going to take a decision that what is the optimum alternatives in the investment sense which you should invest in order to get the best possible returns based on that you are trying to maximize the return or minimize the risk or some combinations of that. And again remember, we are considering in a very simple sense the normal distribution. Now, consider we have projects A, B, C, D. I am considering 4 different decisions and we need to rank them. So, I am not interested for the time being to find out what are the investment which is happening per alternative for the projects A, B, C, D or decisions A, B, C, D. They would be coming out in a later stage. First, I want to rank them provided I have already made an investment. So, consider we have projects A, B, C, D and we need to rank them using the concept of safety first principle. The informations are given. So, along the first row you have basically the RP bar which is the return on the portfolio, the decision for A, B, C, D are given as 7, 10, 12 and 15, and the corresponding second row is basically standard deviation happening for the returns for these decisions which is A, B, C, D, the decisions, and the standard deviations are respectively 10, 15, 15, 105. And you also remember this RL value or RF value which is fixed beforehand by the investor depending on what are the external etc. information which he or she has, the value is given as 7%, and also consider the returns are normally distributed. So, what you need to do is basically again convert them to a standard normal, which I have been doing it time and again in this class by drawing the diagrams. Find out the probabilities based on the safety first principle, find out the probabilities on the left hand side less than RL is given as 7%. So, you can find them and rank them accordingly such that your problem would be solved. Now, as per the safety first principle, so your actual decision is minimize the probability of RP is less than RL, where you have basically 1, 2, 3, 4 till m is the number of projects, and under each project you have the investment we made in jobs, activities or financial decisions or alternatives which are given by j is equal to 1, 2, 3, 14 n. Thus, we have from the basic concept of statistics this rule which we have already done repeatedly. So, this is capital Z, this is small z which is given, that value is alpha can be found out from the standard normal table, rank them from the lowest to the highest depending on whether you are looking at the left hand side or the right hand side. Now, why I am saying in the right hand side, they are depending on many different criteria. If you are considering the negative distribution of the losses, negative distribution being the losses, or if you consider the positive distribution which are the gains, your overall rule remains the same, but with a sign change accordingly. So, it is a maximization problem becomes a minimization or vice versa, and the probability is also rather than on the right hand side you will try to basically look on the rather than the left hand side you will try to look at the right hand side. And you remember that the RPJ for the each investments has have a normal distribution with an average value given by R bar. I am not mentioning the J, and sigma p being the sigma square being the variance of that decisions. Now, remember these standard deviations again I am mentioning, actually they are sigma r of p. So, you are taking the standard deviation of the return of the distribution returns are drawn from, based on that you find out the mean value, based on that you find out the standard deviation. So, once you plug in those values, so you have the value from the project given as corresponding. So, I have taken a different sets of values rather than RL being 7, I have taken 8. The returns for project A, B, C, D or the decisions A, B, C, D are given by 10, 12, 14 and 16, and the standard deviations corresponding to A, B, C, D are given by 12, 17, 17 and 11. Oh, 1 minute, it should be 110, sorry, my mistake, it should be 110. So, based on that the small z values for the first case project is given by 8 minus 10 by 12, for the second one is 8 minus 12 by 17, for the third case C is given by 8 minus 14 by 17, and the fourth case is given by 8 minus 16 by 110. So, once you find out small z, the probabilities can be found out. So, small z's values are given as, I am not saying the minus values because they are on the negative side. So, is 0.17, 0.24, 0.35 and 0.07. So, you want to minimize them. So, obviously, hence project C is chosen according to the principle, the science, because you want to basically minimize the probabilities. So, minus 3.4535 is as far as possible onto the left. So, obviously, the alpha value would be as low. So, if I draw the graph, this is the alpha value, I want to basically make it as low as possible. So, it will be on the left, and based on that you can find out that how we will rank them. So, the ranking system being C is better than B, is better than A, is better than D. Now, I did mention fleetingly the concepts of positive and negative distribution. They were basically based on the fact that whether you have skewed distribution onto the left or the right. I will just draw it in order to make you understand. So, for a positive distribution, these are the axes consider. I will use different colors, skewed onto the left, okay, my mistake, and skewed onto the right. You will have the distributions corresponding to the positive and negative. I will come to that later on in DADM 3, remember that, because in DADM 2 it is more related to the trying to understand the concept of utility theory and how you can utilize it for non-parametric distribution. With this I will end the 10th lecture, which is the end of the second week, and hopefully by 11th lecture, which is the first lecture for the third week, I will be able to wrap up utility and then start in the 12th lecture, which is the second class in the third week, about the actual concepts based on which we will be covering in this DADM 2 lecture series under NPTEL MOOC. Thank you very much for your attention and have a nice day.